Greetings of the day to all of you. I welcome you all to the 12th lecture in the lecture series on basic electrical engineering. In the last lecture, we started off with steady state analysis of AC circuits, where we basically studied sinusoidal excitation, that is, voltage and current signals being sinusoidal in nature. We discussed the advantages of having sinusoidal AC waveforms, and we also studied the basics of phasor analysis and some basic idea on complex numbers and their role in phasor analysis. Today we are going to study about the phasor relationships in circuit elements. So basically we will analyze the relationships between voltage and current phasors in different types of circuits, whether they are resistive, inductive or capacitive circuits. Let's first begin with a very simple circuit, that is your resistive circuit. An AC circuit with a resistance as your load element. We assume that the source is sinusoidally excited, so the voltage here is assumed to be sinusoidal. For convenience, let's assume a sinusoidal signal without any phase delay, so Vm sin omega t. We know that the current flowing in this circuit, let's call it I, will vary as Vm sin omega t by R, and you may also call Vm by R as Im sin omega t. So this is time domain analysis, where both voltage as well as current are treated as variables that are time dependent, and we are seeing their response in the time domain. Now in this case, if you would like to draw the waveform of voltage, that is Vm sin omega t, we know that it would look something like this. Assuming that this is the omega t axis, and these are the pi and 2 pi points, and the peak value is Vm. Now if this is the voltage signal, the current signal is going to be simply Im sin omega t, scaled version of the voltage. So again a sinusoidal signal with peak value equal to Im, where Im is simply Vm upon R, where Vm denotes the maximum value of the voltage signal. Now this is a basic current voltage relationship in a simple resistive circuit in the time domain. The same information should be preserved in the phasor domain as well. So if we do the same analysis in the phasor domain, we can represent it as the voltage phasor being equal to the current phasor into the resistance of the circuit. The simple Ohm's law, right? So we can say that if the voltage phasor is like this, let's call it V, then the current phasor is going to be in the same phase as voltage, just scaled by the value 1 upon R, or you can say V is scaled by R. This is about phasor relationships in a simple resistive circuit. But you know that there are other elements, especially when we talk about AC circuits, there are other elements such as the inductance and capacitance. Let us now consider an inductive circuit excited by the same source, Vt being equal to Vm sin omega t. Now if the element over here is an inductance which is excited by a sinusoidal source Vm sin omega t, then in that case we know that this inductor is dictated by the relationship Vt is equal to L di by dt, right? Or I can say that the current response of the circuit is going to be 1 upon L integral of Vt with respect to t. If we integrate the voltage vector, the voltage signal, we get Vm cos of omega t by omega, and then there is a minus sign, something like this. So this is my current response IT, or I can say IT is equal to Im, where Im is Vm by omega L, and minus of cos omega t, I can write it as sine omega t minus 90 degrees, right? Now I have voltage being Vm sine omega t, and I have calculated IT as Im sine omega t minus 90 degrees, where Im is simply the constants put together. Now let's analyze this thing, this time domain analysis on graphically. So we have the voltage signal, which is a sinusoidal signal with a peak value of Vm. And if this is the omega t axis, then I know that these points are pi and 2 pi. From this time domain analysis, I know that the current signal is simply Im sine omega t minus 90 degrees, or you can say it's a minus of cos signal if you use this equation. So minus of cos signal, which is something like this. Right? So this signal is your current signal with peak value being equal to Im, where Im is Vm by omega L, and this signal is actually lagging the voltage signal by 90 degrees. So the voltage signal had a phase of 0, and the current signal has a phase of minus 90. So it is lagging, or you can say that it reaches the peak 90 degree later than the voltage signal. So you have a phase difference of 90 degree lagging current. The current is lagging by 90 degrees behind the voltage. And this is a characteristic behavior of your inductance. Now, if I say that I want to get the same information in terms of phasors, how do we put it? Let's see, this was all time domain analysis. Now let's repeat this analysis in the phasor domain. We know that the voltage phasor is V, and the current phasor, the current through the circuit, is a capital I. And we also know that the inductor is determined, it follows the relationship L di by dt is equal to V. Now, if the relationship between voltage and current, we know that it follows the simple differential equation, and we also know that if the time domain current I of t is represented by the capital phasor I, then di by dt will simply be represented by j omega I. In the phasor domain, this information will be written as L into j omega I, where I is the current phasor, is equal to V, right? So I can say that for an inductor, V, the voltage phasor, and the current phasor are related by V is equal to j omega L into I, the relationship between voltage and current phasors. If I want to represent it graphically using phasors, it means that if this is my voltage phasor, I don't have space, let's do it elsewhere, maybe here, yeah. If this is my voltage phasor V, then my current phasor will simply be V upon j omega L, or you can say minus j V by omega L, right? It means that the current phasor will have an angle of minus j, that is minus 90 degrees. So this is my current phasor. Its magnitude will be V by omega L, and its phase will be minus 90 degrees. So this is a phasor representation of what we just now represented in the time domain, and this is a phasor representation of voltage and current in a purely inductive circuit. Again, the minus 90 degrees tells you that the current is lagging behind voltage, right? So this is about phasor relationship with an inductive circuit. Now let's move on to a capacitive circuit. So here we have a capacitance in an AC circuit excited by a sinusoidal voltage source, and we have to see the voltage the relationship between the voltage and current in the circuit. We know that the source is excited by a voltage v of t, which is equal to Vm sine omega t. And we also know that if we do the time domain analysis, we also know that C dV by dt is equal to I in a capacitor. The relationship between a capacitor follows this equation. Now, if I want to find the current response I of t, it will simply be equal to C and the derivative of Vm sine omega t. That will be Vm into omega cos of omega t. Right? Or we can also write it as I of t is equal to Im into sine of omega t plus 90. Right? Now, if I represent this graphically, then I have a sinusoidal voltage signal. My excitation signal is sinusoidal with a peak value of Vm, and this is the omega t axis. This is my voltage signal. Then this equation tells you very obviously that the current is a cosine signal, or you can say it is sine omega t plus 90 degrees, which also means that it is leading. This is Im, and its magnitude is CVm omega, the magnitude of Im, and it is also leading. It is reaching its peak 90 degree earlier than the voltage signal. So it is leading the voltage signal by phi, which is equal to 90 degrees. So it's a 90 degree lead, right? So my current signal in a capacitive circuit is leading the voltage signal by 90 degrees. Now the same information I want through phasor analysis. This was all time domain analysis. The same analysis we are going to repeat with phasors. Now I know that the voltage phasor and the current phasor will retain the relationship like this. However, when you do the differential, we know that it is j omega v is equal to I. We have done this in the previous class, how differential operator in the time domain actually translates to multiplication by j omega in the phasor domain. And from this we can say that, we will get the relationship between V and I, the phasor relationship between V and I in a capacitive circuit. Now, let me again assume that this circuit is excited by a voltage phasor V, whose phase I have assumed to be 0 and a specific magnitude. Now, the current will simply be V phase shifted by J, and J means 90 degree phase shift in the leading direction. So we have V phasor looking like this, and I phasor will be 90 degrees leading over the V phasor. The magnitude of the I phasor will be equal to V omega C, and the plus J multiplication by plus J simply means a leading angle of plus 90 degrees. So this is the phasor representation of the same thing. Now this was all about phasor relationships in basic circuit elements such as R, L and C. I think it is the appropriate time to introduce the concept of impedance in AC circuits. So let's talk a little about impedance in AC circuits. Just like you have resistance in DC circuits, the correct term to use in AC circuits is impedance, which is simply the opposition to the flow of sinusoidal currents in AC circuits. It is denoted by Z, and it is actually physically equal to the ratio of voltage phasor by current phasor. Right, so it's nothing but the equivalent of resistance in DC circuits, that is the opposition to the flow of sinusoidal current. When we're talking about AC circuits, that is your impedance Z. Now, just now we did some voltage and current relationships. In a resistive circuit, we know that the phasor relationship is V is equal to IR. In inductive circuits, we know that V is equal to I into J omega L. And in capacitive circuits, we know that V is equal to I upon J omega C, right? Now, if we simply find Z, which is V upon I, in this circuit, resistor circuit, Z is going to be, the impedance is going to be equal to the resistance. In case of an inductive circuit, the impedance is going to be J omega L. And in case of a capacitive circuit, the impedance is going to be 1 upon J omega C, or you can also write it as minus J upon omega C, right? However, all types of circuits are, most types of circuits, they are not just resistive or just inductive or just capacitive. You may have a combination of resistances, inductances, and capacitances in your AC circuit. In that case, your impedance will be a combination of all these elements. But before we do, we go into, those kind of circuits, I would briefly tell you something about the role of frequency in impedance. If you observe the resistive circuit, when you talk only about the resistance, the frequency has no role in calculating the impedance. However, if you talk about an inductive circuit, it's not just the value of inductance, but also the frequency of your supply that determines the impedance. Similarly, when you talk about capacitive circuits, it's not just the value of capacitance, but also the frequency of your excitation or your AC voltage that determines the impedance to the flow of sinusoidal AC currents. Now, if I say that my circuit is purely DC, say if it's DC, then I know that the frequency omega is 0, right? Now, if omega is 0, it means that if the circuit is resistive, obviously the impedance is the same as the resistance, that is R, but the inductive impedance in that case will become 0, and the capacitive impedance in that case will tend to infinity. What does this tell you? It tells you that in DC circuits, the resistance offered by a resistor is same as the impedance offered by a resistor is same as a resistance. And in the same DC circuit, the impedance offered by an inductance is 0, which means that an inductor in a DC circuit behaves like a short circuit. So it's a short circuit. And the impedance offered by a capacitor in a DC circuit, we're talking about DC when omega is equal to 0. The impedance offered by a capacitor in a DC circuit tends to infinity, which means it offers a very, very large impedance, or you can say that a capacitor in a DC circuit behaves like an open circuit, right? So in a DC circuit, the resistance is as it is, the inductance is a short, and the capacitance is open. It's as good as saying that it will not allow any current to flow because it will offer infinite impedance. Now, if we talk about the other end, we did talk about zero frequency. Now, what if we talk about the other extreme, that is frequencies, very high frequencies, AC signals, but not at 50 Hertz, but at very, very high frequencies. So let's discuss what happens when frequencies are very high, which is omega is very high. A resistive circuit will continue to offer impedance equal to its resistance because I said it is independent of frequency. However, if the frequency of your AC voltage source, the sinusoidal voltage source is very high frequency voltage source, the sine wave has a very high frequency, then the impedance offered by the inductance is going to be very high. And it is possible that it may not allow current to flow. It may, if the frequency is very high, then it is possible that your inductive circuit may behave like an open circuit because it's offering a very high impedance to high frequency AC signals. And if your frequency is high, then the capacitive circuit will offer a very small impedance, because it is 1 upon omega, inverse relationship with frequency. So the frequency is very high, Z is very, very low, or you can say that it is possible that the capacitor will allow all, it will be nearly a short circuit, or you can say that it will allow all high frequency components to flow through it. It will allow them to flow, and the inductor will block them, or it will open circuit them if they are high frequency components. So this was about impedances in AC circuits, and that the impedance of inductors and capacitors is frequency dependent. Now let's talk about circuits where you have a combination of R, L and C. Then in that case, the relationship for impedance continues to remain the ratio between V and I, but the impedance Z will have both real and imaginary parts, which means that Z will be represented by R plus JX, where R is the effective resistance and X is the effective reactance of the circuit. When we do questions on this, you will probably understand this better. The reactance may be inductive or it may be capacitive, because we know that J is introduced by L and C elements, right? So if you have inductance and capacitances, obviously one is contributing to plus J and the other is contributing to minus J, so they tend to oppose each other, but the net X will depend upon the total inductances and capacitances connected in the circuit. So the imaginary part of the impedance is introduced by reactive elements like L and C, and it is called as reactance. X is called as reactance, and the real component of the impedance is introduced by resistances, and needless to say, it is called as the resistance itself. So resistance is the real part of Z and reactance is the imaginary part of Z. If you represent, this is the rectangular form representation of the complex number. If you represent it in terms of the polar form, then it is simply magnitude of Z at an angle of theta, where magnitude of Z is equal to under root of R square plus X square, and theta is simply equal to tan inverse of X by R, right? If I have information about theta and magnitude of Z, but I do not know R and X, then I can find R and X as R is Z cos theta and X is Z sin theta. So that is about finding R and X of a circuit if I know the magnitude of their impedances. This also brings us to another important concept, that is admittance. Just like impedance is, demonstrates the opposition to the flow of current, admittance demonstrates the ability to allow current. So naturally, admittance, or Y, is the inverse of Z. In resistive circuits or in pure DC circuits, the impedance is nothing but the resistance, because L and C do not have roles to play there. And the admittance is in DC circuits is often referred to as conductance, where conductance is simply 1 upon R, right? So when the same information is translated in the AC domain, where we have all kinds of resistances, inductances, capacitances, both imaginary and real components of impedance, then we have impedance being equal to V upon I and admittance being equal to 1 upon Z, or you can say I upon V, right? So let's just say that the admittance is, again, obviously because these are complex numbers, and so the admittance y will also be a complex number, that is g plus jb. This is how it is represented. And no, g is not equal to 1 upon r, and b is not equal to 1 upon x. This is a confusion that many students tend to do, but please be sure and aware that they're not independently, the real part is not independently the inverse of the real part of z, and b is not 1 upon x, that is imaginary part of 1 upon imaginary part of z. It's not equal to the inverse of that. But what is actually true is that y is the inverse of 1 upon z, which is the inverse of z, which is simply 1 upon r plus jx. If I multiply it by r minus jx on the numerator as well as denominator, then I will get g plus jb is equal to r upon r square plus x square minus j times x upon r square plus x square. So this tells you that g, in fact, the admittance, if you have to find the admittance of the circuit, y, which is denoted by mho or Siemens, it is g plus jb, where g is equal to r upon r square plus x square, and b, the imaginary part, is equal to minus x upon r square plus x square. G is known as the conductance, and obviously if it's just a resistive circuit, it will be equal to 1 upon r when there is no x. In that case, the conductance is nothing but 1 upon r, but if you have x, then the conductance is r upon r square plus x square, and g is the conductance, and b is known as the susceptance. And together they form a complex number, that is the admittance of the circuit. Now that was all about phasor relationships and the concept of impedance in your AC circuits, as well as the concept of admittance in AC circuits. We will do a small question that will help you clarify the concepts that we have studied in the past 2 lectures. So you essentially have, let's do this question, you essentially have an AC excitation, and you have a resistance as well as an inductance in the circuit. We are operating in series. The value of the inductance is 0.2 Henry and the value of the resistance is 4 ohm. The AC voltage source is 20 sine 10t plus 30, and this is the current IT flowing through the circuit, and this is the voltage across the inductance is defined as V of t, the voltage across the inductance, right? You have to find both IT as well as VT in the circuit using, of course, phasor analysis. You can also use time domain analysis, but we want to see how to use phasor analysis. So we know that the source voltage, let's call it Vs, is equal to 20 sine 10t plus 30. In order to represent it like a phasor, it is convenient to use the cosine representation. So I can write it as 20 cos of 10t plus 30 minus 90. Cos of theta minus 90 is sine of theta. So you have this as 20 cos of 10t minus 60. In terms of phasors, I can write it as 20 at an angle of minus 60. So I have information of the magnitude and the phase. Frequency, I can just remember that omega is equal to 10 for my circuit, right? So I just remember that information, and the phasor is preserving magnitude and the phase. So this is my source phasor, and now I have to find IT, which is the current phasor. The current phasor I will be equal to the voltage phasor 20 minus 60 divided by the impedance V upon Z, and the impedance will simply be 4 ohm plus J times omega L, because omega L is the impedance of the inductive circuit, right? So you can say it is 10 into 0.2. I can use a calculator to find my current phasor. So you have to use a calculator like I've shown. In the mode, choose your mode number 2, that is complex, so you can do complex analysis. 20 at an angle of minus 60 divided by 4 plus 2 iota. You can convert this rectangular form into polar form by doing shift complex r at an angle of theta, and this gives you as I being equal to 4.47 at an angle of minus 86.56 or 57. So your current phasor is 4.47 at an angle of minus 86.57. If I want to write it in the time domain, I can write it as 4.47 cos of omega t, that is 10t, minus 86.57. If, however, I wish to write it in the form of a sinusoidal signal rather than a cosinusoidal signal, because all my data was given as sine waves, I can simply convert it using trigonometric identities as sine of theta plus 90, so that is 90 minus 86.57, that is 3.43, so that is 10t plus 3.43. So this is about the current signal IT, which I have already found. Now I have to find VT. VT I can find, again use phasor analysis. The phasor V will be equal to the current flowing into the circuit into the impedance offered just by the inductance, because that is the voltage across the inductance. So VT will be I into J omega L, right? My I phasor is, I have already calculated IT, right? This is one of the answers, so I'm removing it for now because I don't have space. My I phasor is 4.47 at an angle of minus 86.57. So my V phasor will be equal to 4.47 at an angle of minus 86.57 into J omega L. Omega is 10, L is 0.2, 10 into 0.2 is 2, so into 2J. Or you can also call 2J as 2 at an angle of 90, because J is nothing but 1 at an angle of 90 degree. So if we move further, we can simply calculate this product as 4.47 at an angle of minus 86.57 into 2 times J, 4.47 at an angle of minus 86.57, and that is 8.94 at an angle of 3.43. That is my voltage phasor. If I want to write it in the time domain, I can say 8.94 cos of omega t, that is 10t plus 3.43, or I can say in terms of the sine wave, it is 8.94 sine of theta plus 90, that is 10t plus 93.43. So this is my voltage across the inductor in the time domain. I have done all the analysis is in the phasor domain, and then return back to the time domain just to get the answers. So maybe solving a few more questions on this will help you understand it better. So this was all about phasor relationships in AC circuits, basic phasor relationships in resistors, inductors, capacitors, and how we apply phasor analysis in a circuit containing all these elements. We also discussed the concept of impedances and admittances. And I guess that's all for today. I wish you all the best. If you have any queries or doubts, please feel free to contact me on the WhatsApp group.